Okay, yeah. So your quiz rather, will come from the past 5 years of exams, so fall 17 through fall 21. Um, it is split between exam 3 and 4 a little bit. So exam 3 and then exam 4. For fall 17, it's 1 through 10 on exam 4. Oh, there's a seat over there. 8 through 18 on the fall 18 exam. On fall 19, it includes numbers 18 and 19 on exam 3. Those are the only exam 3s. And then 1 through 6 on exam 4. Uh, on fall 20, it is 11 through 24. And that's on exam 4A. That semester, I was trying something different where I split up the exams into two parts. So that's what that's all about. And then I kind of like that actually, but the students didn't like it. And then I had 11 through 19 for exam 4 from last year. Okay? So those are all the questions. Look, about 40-ish questions there for you to review over the weekend, and I will take those directly for the quizzes, okay? And then knowing those will really help you for the exam coming in a week or two, whenever that is, a couple weeks. All right? You all good on that? All right. Questions. Specific questions that you have?
Not really like a question, but for the quiz, it's gonna be chapter
8.
8, just chapter 8.
Just chapter 8. I will give you the equations for chapter 7 and 8 because sometimes those things intermingle a little bit. All right?
Scroll down.
Yeah. For this,
Yes.
do you want me to get in there? Do you want me? No. Do you want me in there? No.
Sure. Go.
I'm just joking. All right. Specific questions, John? Okay, well, I can just go through and we'll do some that I think are not ones that are on the quiz. I haven't made the quiz yet, but that sometimes give students difficulty. Is that okay? All right. Well, you're certainly going to see some moment of inertia problems. So um, let's look at this one, number 12. Number 12 is, oh no, let's go down to another example. Okay, so we'll go to the fall 2019, which was it's called spring 19, but it's really fall 19. This was our last normal semester before we entered into the age of COVID and Ida. So, variety of moment of inertia problems, like number 3. I always give a problem like this on exams where I give you some irregular shape and ask you to rank the moments of inertia. Really like these problems. In problems like number 3, what you want to do is to, well, a couple things. Look for the moments of inertia that's either biggest or smallest. And the point that's in the middle of the object will always be the smallest moments of inertia because that minimizes the value for r the most. Right? The biggest moment of inertia, on the other hand, is always going to be the point that's far away from the furthest point in that object because that makes r bigger. Right? Because we have this dependence on r that is quadratic, that if I make r bigger, that makes I even bigger, right? If I double r, it quadruples I. And so I want r to be as big as possible in order to get a big moment of inertia. So I look for the biggest and the smallest. Since the smallest is A, that gets rid of these 3. The biggest is, well, this says D, but notice that points B and D are the same. Symmetrically, they're the same. And so that gives me the answer that A is less than C is less than B is equal to D. So looking for those things that look equal or looking for the biggest or smallest moments of inertia, that's really how you approach these ranking questions. Also, you will have to find the moment of inertia of an object. Let's see. Well, number 5. This is actually a combination of 2 problems. Hey guys, there's a chair over there, and one of you can have this stool. Yeah. Sorry, but no. Well, here's a. If you want to take this table, that's fine. You can take that table. You can just sit right there if you want. Okay. So let's look at number 5. This is a two-step problem. So first, I want to find the moment of inertia, and then I want to find L. And L is equal to I omega, because I'm asking for what is the angular momentum. That is L, is the angular momentum. So I have a 2-kilogram particle that's attached to a rope, and it's spinning 3 meters from a vertical axis. So we want to look at our equation sheet. You're going to have, like I said, chapter 7 and 8 on that equation sheet. But when I'm doing moment of inertia, remember there are two different approaches. One is that I'm finding the moment of inertia of a regular shape. So if I have a disc, like a merry-go-round, or like a flywheel, you'll see a flywheel, that's always going to be the cylinder of radius r. A disc or something that's round and flat is just a really flat cylinder. Or if I have a sphere of a certain type, or a bar, or a hoop, or a wheel, you can find those all here. But in this case, I have a particle that's rotating about an axis, and that's going to be given by that equation. That is our basic definition of what is I. So I can find the moment of inertia of this object is just going to be the sum of mr squared. Can you go in the lab and pull a stool out of the lab? There should be some in there somewhere. Just keep walking down and you're going to find one. All right, so anyway, I is equal to the sum of mr squared. So that's going to be 2 kilograms times 3 meters squared. That's 2 times 9, or 18 kilogram meters squared. So that is the moment of inertia for this object. And then if I want to find L, then I just say L is equal to I times omega. That is going to be 18 kilogram meters squared times omega. Omega is equal to 4 radians per second, which is, so that's 4. 4 times 18 is 72. So B is the right answer for that one, for number 5. So that was a two-part problem, and you see other problems that are similar to this, where you have to find the moment of inertia of an object. In this case, you need to identify, is this a regularly shaped object, hoop, sphere, disc, hoop, or bar, or is it a particle? And you know that this is a particle because I just give you, I don't describe the shape of this actual object, I just say it's an object, and it's a certain distance from the axis of rotation. Okay? Hold on just a second, let me check my student. Got it? Sorry. All right, other types of problems that we'll have, well, are like moments of conservation of angular momentum, like this number 6, where I have this mass that moves from a distance to a distance of 1 meter to the rotational axis. So up here, we had to find the moment of inertia. We'll say that that's our initial moment of inertia. Our final moment of inertia in this case, because it moves to a new distance, is going to be equal to mr squared. That's going to be 2 kilograms times 1 meter squared. So it's sort of like the figure. Brianna, listen, you go grab a stool out of the physics lab and then bring it in. I'm sorry. And so that's going to be equal to 2 kilogram meters squared. So my moment of inertia has gone down by a factor of 9. That means that my speed is also going to change by a factor of 9. Do you think it's going to go up or down? Is my speed going to go up or down?
Your moment of inertia is the same?
No, my moment of inertia has gone from 18 kilogram meters squared to 2 kilogram meters squared. It's going to go, the speed is going to go up, because here L is equal to I times omega. If the moment of inertia goes down, as it does, actually, let's see, yeah, my moment of inertia goes down, that means that omega goes up. This isn't working out right. Maybe I had a mistake here. Hold on, let me see. Number 6 should be 8. Hmm.
4 times 9 is 36.
4 times 9.
Or if you set the L as the 72 equal to 2 omega, that equals 37.
Oh, right. Yes, thank you. Yeah. All right. All right. So that is my moment of inertia. Now, L is still equal to 72 because momentum is conserved. And so that's equal then to my I final times my omega final. So 72 is equal to 2 times omega final. And so omega final is going to be 36 radians per second. Okay? Listen, I encourage you to, when you work on these problems, that you do it just like this, that you write out the equations, you write out what you know and what you don't know. I do find that students often that if they don't write down what they're thinking in their heads, and I know that a lot of you do that it often backfires on them because they'll make a mistake in their calculator or they're just not thinking of something correctly. But often when those students write those things down on the paper, that they see their mistakes more readily. So if you're one that's just been not doing well in quizzes and exams, try that. I think it will really help you to write down, draw pictures, write the equations that are relevant, write down the things that you know, write down the things that you don't know. Really follow that model for approaching these types of problems. I'm confident that it will help many of you. Okay? And I know some of you, you don't really know what's going on. Like you seem to know it, and you practice it at home, and you do just fine. But then when you come into the exam or the quiz, I mean, who else is that? Is that just me? Or yeah, I know it's a lot of y'all. And so try that. Like as you're practicing, print out the things on paper. Okay, if you don't have access to a printer, you come see me. Print them on paper. Practice them like you were in the classroom. Set aside a time devoted. Use those videos, but only use them as a last-ditch effort. Like you have no idea what's going on, and you just want to see, sort of, get a little hint or bump in the right direction. Okay? Watching the videos is not going to help you. Just sitting there and watching them, it goes in one ear and out the other. Okay? So practice them on your own. All right, let's look at some others here. You're going to have some energy stuff. Let's look at number 1. Remember, we worked one like this last time in class where you find the total energy. If it says total energy, that should be a key in your head to think, oh, this is asking for the rotational energy and the translational energy. If you see total, that's what you're thinking. So my kinetic energy is going to have 2 parts, the rotational and the translational kinetic energy. That rotational kinetic energy is 1/2 I omega squared. That equation is on your equation sheet. And the translational is 1/2 mv squared. That's like what we had in a previous chapter. A couple of things we need to do here because I don't have all of this information. The first is to find I. This is a hoop. So I look on my equation sheet, and the equation for a hoop is going to be m times r squared. So that's just mr squared. It has a mass of 20 kilograms, and 4 meters is the radius. Check, sometimes I give the displacement. If you've been practicing, you've seen a couple problems like that. Not the displacement, excuse me, the diameter. Usually if that's the case, if it's something sort of not standard, I'll highlight it and bold it and make the font bigger. Just read every word. Every word's important. So that moment of inertia is 20 times 16. That's 320 kilogram meter squared. Then I don't know omega, but I know the velocity, and I know that the velocity is equal to omega times r. So omega then is equal to v divided by r. V is 2 meters per second divided by r, which is 4 meters, so that's 0.5 radians per second. So now I have everything that I need. I have I, and I have omega, so it's going to be 1/2 of 320 times omega, which is 0.5 squared. That's a quarter of 160. That's 40 joules. And then this is going to be 1/2 of the mass, which is 20 times v squared, which is 2 meters per second squared. That's 10 times 4. That's 40 joules as well. So the total energy is 80 joules. We did a very similar problem in class. It was in your homework problem. You'll probably see, if you don't see it on the quiz, you'll see something like it on the exam. Remember, total energy is the rotational plus the translational, and then usually in these problems you have to do these maneuvers to figure out either omega or v, and I'll just give you one of them. These equations for translating v to omega, that's in the chapter 7 work, which you'll have that on the quiz. All right. These problems, like number 2, often give students difficulty where you're thinking about how much does the energy increase when you have this constant angular momentum. So I find that it's helpful first to write down the conservation of angular momentum. That is, I omega is equal to I omega. Right? This was the total angular momentum is always the same in scenario 1 and in scenario 2. So here I have a spinning object and the angular speed increases by a factor of 3. So omega is going up by a factor of 3. That means that I has to have gone down by a factor of 3. In order for that to remain constant, that's what happens. If one goes up, the other goes down. And now knowing that, I can look at my rotational kinetic energy. That's 1/2 I omega squared. And I now know how these two variables are changing. And so I can just put those amounts that they're changing into this equation. There's a third right there. This is 3 times right here. So I have a third times 9, right, because the 3 is squared. Since I do that to the right-hand side of the equation, I also have to do that to the left-hand side of the equation. So the energy has increased by a factor of 3. If omega is increasing and I is decreasing by the same amount, because omega is squared, that means your overall kinetic energy is going to go up. On the other hand, if omega is decreasing but I is going up, your rotational energy is going to go down. Right, so that omega really carries the day because it's squared. Whatever it does, if it's going up, energy is going to go up. If it's going down, energy is going to go down.
So you don't have to worry about the half?
Don't have to worry about the half. So here I'm just looking at a relationship between these two sides of the equation. This half is just constant. Okay? I'm looking at how much does this variable change and how much does this variable change. And then that tells me how much this variable also has to change. Okay? I know that half throws people off. It did several other people too. But no, we don't have to think about that. This is just a constant. Okay? Let's look at number 4. This is a good exam. You will have questions from other exams, but this fall 19 is a good one. A solid sphere has a moment of inertia of 500 kilograms and a radius of 5 meters, and then engages with a hollow sphere with the same radius and mass. And I want to know, what is the new moment of inertia? So this is like the Richard Pryor thing where we had 2 parts coming together. In that part, it was a cylinder and a wheel. And to find the total moments of inertia, we just added them together. Similar thing here, where these 2 objects are coming together, and I want to know the total moments of inertia. So I need to go back to my equation sheet and look for the solid sphere, which is 2/5 mr squared, and the hollow sphere, which is 2/3 mr squared. So the solid is 2/5 mr squared, plus the hollow is 2/3 mr squared. Made it easier here because they both have the same mass and radius. So I just put in that mass of 500 and radius of 5. So I get 2/5 of 500 times the radius squared, which is 5 squared, plus...
The inertia was 500.
Oh, yeah. Okay, so this is... thank you. You should read every word, right, Emmy? Yeah, so I have to figure out what the mass is from the first one. So the solid sphere has a moment of inertia of 500 kilogram meters squared. That's equal to 2/5 times the mass times the radius squared, which is 5 squared. Let's see, I can get rid of this 5 with one of these. And so M is equal to 50 kilograms. All right, so I have then, for the total moment of inertia, I have 500 plus 2/3 of 50 times the radius squared, which is 5 squared. So that's going to be 50 times 500. I think it's E. Is E the right answer, do y'all know?
So it's not D or C.
And it can't be D or C, right? 2/3 times 50. It is A. Okay. All right. This is a good problem too. Let's look for one because they come up with conservation of angular momentum. But first, are there any other questions sort of about these questions that we see? Yeah, Jadecia? Number 2. Yeah, those are hard for students. Let's look. But I like them. You'll probably see something like that. Yeah, so number 12 is similar but different. So in number 12, it says a figure skater pulls her arms in to decrease her moment of inertia by a factor of 2. First, write down my I omega. That is my angular momentum. She is decreasing her moment of inertia by 2 times a half. That means that omega is going to go up by a factor of 2. Then the kinetic energy is 1/2 I omega squared. So my I is changing by a factor of 1/2. My omega is changing by 2. So that's 1/2 times 4. So my kinetic energy is now twice what it originally was. So the energy has increased by a factor of 2, which jives with what I think it might mean, because you pull your arms in, that makes your I go down, so you spin faster, and since that energy is dependent upon omega squared, even though I is going down, omega is going up by the same amount, but because it's a quadratic relationship between k and omega, k is ultimately going to go up. Let's see if there's another one, that number 10. Number 10 is from chapter 7. Not going to see it on this.
I was just looking at that.
Okay. Can we do number 16? We'll go to another exam. There's another one like that I want y'all to see. Number 16 is where I have a bar that engages with a flywheel. Now, a flywheel is a disc. Y'all know what a flywheel is when I say flywheel? Engines often have flywheels in them. Big turbines, like if you have a big energy producing plants, they have flywheels. What they are these big steel discs that rotate, and they're used to store rotational kinetic energy. So they get them to rotate, and then when they need to use that energy for something, to spin a turbine, to make your car go faster or whatever, that it uses that energy and transfers it into whatever system you need to transfer. Anyway, it's a disk. So I have a bar and I have a disk that are rotating. And I want to know when they engage, then what is their new angular speed? This is like a perfectly inelastic collision. It is a perfectly inelastic collision. Remember those that we saw where the two objects stuck together and they move off at the same rate? That's what we're dealing with here. So I have the angular momentum of the bar, I omega bar, I'll call it, plus the angular momentum of the disk is equal to angular momentum of the combined system. So the bar has a moment of inertia of 8 kilogram meters squared, that's given right there, and it's rotating at 2 revolutions per second. So that's 8 times 2, plus the moment of inertia of the flywheel is going to be 16 times omega. Now we have to be really careful here, because notice that this is in the counterclockwise direction, so the 2 is positive, but the flywheel is going in the clockwise direction. So this is going to be a negative 2 revolutions per second. And then that's going to equal to the final, thank you, 4. 4 revolutions per second, but it's negative because it's clockwise. And then the combined I is going to equal to 8 plus 16. Those two things come together. The bar and the flywheel come together. 8 plus 16 is 24 times omega. So that's 16 minus 64 divided by 24 equals 2 omega. What's that? Oh, that's 2. Yeah, so that's negative 2 is equal to omega. Because it's negative, that means it's clockwise. So E is the right answer. You almost certainly have a question like that. I don't know that you'll have that particular problem, but that is a conservation of angular momentum problem. That's just like the problems that we did with the colliding balls, okay? It's that we're looking instead at the angular momentum. I omega plus I omega equals the final angular momentum. All right? Other questions, y'all? Go through. You will have a torque problem, so let's do one of those. Let's do like number 23 here. So this is, what exam was this, do you recall? It's fall 2020. Let's do number 23 and 24, because you'll almost certainly have a problem like this. You'll have it on the free response too. So I have the first problem is just ask what is the net torque acting on this object. Notice that there are 3 forces, and you'll have a similar object, and there'll be 2 or 3 forces. Almost always one of those forces does no torque at all. And it'll, in a couple ways, it'll do no torque. Either the force will be acting at the axis of rotation, in which case R is equal to 0, so torque equals 0. Or you might have a force that's acting at an angle of 180 degrees, and this force that I drew is not in the problem, but that force would also have a 0 torque. So in this case, I only have 2 objects, or 2 forces that are causing a torque. I'll call this one torque 1. I'll call this one torque 2. Now I need to figure out, are they positive or negative torques? So if I imagine this first force pulling up, that's going to cause the object to move in a clockwise direction. So this is going to be a negative torque. This one causes the object to move in this direction. So that's going to be a counterclockwise force, counterclockwise torque, so it'll be positive. So this one's a negative torque, and this one's a positive torque. It's very important that you get the signs correct.
What is the middle one?
The middle one doesn't provide any torque at all because it's at the axis of rotation. And at the axis of rotation, R is equal to 0. It would like being trying to open a door by pushing right here. I'm never going to cause any rotation. As hard as I push, no rotation. But if I push down here, I can cause rotation. Likewise, the force at the end, if I try pushing like this on the door, no rotation, because my angle is 180 degrees. And the sine of 180 is equal to 0. So 2 ways you can have no torque from a force: at the axis of rotation, or at an angle of 180 or 0 degrees. Next, I want to calculate the net torque. The net torque is going to be negative torque 1 plus torque 2. That's going to be negative 25 times the distance. That's the distance from here to the axis of rotation, which is 2 meters, plus 10 times this distance, which is 1 meter. So that's negative 50 plus 10, that's negative 40 Newton meters. That's 40 Newton meters clockwise. Sometimes I do give the same number, but they'll either be clockwise or counterclockwise, so just be careful on that. And then the next part is finding the angular acceleration of this bar. Now I give you the moment of inertia right here. In fact, this bar is not in our equation sheet because the bar that we have in the equation sheet rotates about an axis in the middle. So you could calculate the moment of inertia of this bar, but you have to integrate over the length of the bar. I'm not going to make you do that. So I gave you the moment of inertia for this bar, and I want to know what is its angular acceleration. I know that the torque is equal to 40 Newton meters, and I know that that's equal to I times alpha. That's our Newton's second law for rotational motion. So our torque, which is 40, is equal to I, which is 3 times alpha. So 40 divided by 3 is 13 radians per second squared. And that rotation is going to be clockwise. So if I ask for the sign or the direction, it will be clockwise or it will be negative. But in this case, I wasn't looking for that. Okay? Let's do a couple others. Oh, this is exam 4, but you don't have anything for that. Any particular questions that y'all have? Okay, let's just do one or two more and then I'll let y'all go. Okay, let's look at number 11. This is another one of those like you had asked about, Stacia. So I have an object that's spinning at a constant rate and has a rotational kinetic energy. It increases its moment of inertia and its angular velocity decreases by a factor of a half. What is the new kinetic energy? So this is what's going on. I have I omega. The velocity goes down by a factor of a half. That means that I must have increased my moment of inertia by a factor of 2. So that's the skater putting their arms out. They slow down, that means they've increased their moment of inertia. So the new kinetic energy, which is 1/2 I omega squared, omega changes by a half, I changes by 2, that's 2 times a quarter, which is 2/4 or 1/2 of the total energy. Y'all see how I did that, right? Yeah? Okay. Because I have this half squared, which becomes 1/4 times 2. 2 times a quarter is equal to a half. All right. There's another total energy problem. Another moment of inertia. Let's just try this. Which one of these has the biggest moment of inertia? A, B, C, or D? C, because it has the biggest moment arm, okay? So I can get rid of B, D, or B, C, and this one. And then B has the smallest moment of inertia. That doesn't help me because they both have B. So now it's either A or B. Which one is either these two? Which one is bigger here? A is going to have the bigger moment. Excuse me, A and B. Which of these has the bigger moment of inertia? D, right, because you notice this distance is bigger than the biggest distance for A, okay? So you want your axis of rotation to get as far away so that you get a really big moment arm. So D is bigger than A, so A is the right answer there. All right, number 15 is another one like we worked where those two objects are coming together. That's a perfectly inelastic collision. Let's look at number 16, and then I'll let y'all go. So two disks, A and B, have the same momentum. That means that I omega is equal to I omega. But the radius of disk A is twice the radius of disk B. So I'm going to draw disk A over here. This is disk A. This is disk B. Both have the same mass. If the angular speed of disk A is omega, what is the angular speed of disk D? So I need to think about how their moments of inertia are different. I know that moment of inertia is equal to 1/2 mr squared. Let's say that this is moment of inertia I. What is going to be the moment of inertia in relation of disk A? The first, is the moment of inertia going to be bigger or smaller? It's going to be quite a bit bigger. It has twice the radius, so it's going to have 4 times the moment of inertia. So if I have 4 times the moment of inertia, well, let's see. I'm looking for the angular speed of disk B. I should have done this the other way. But disk B is going to spin faster or slower?
Faster.
It's going to spin faster. It has a smaller moment of inertia, but the same angular momentum, and it's going to spin faster by a factor of 4. Those problems are hard, but drawing pictures will really will really help you. Drawing pictures will help you to understand them, okay? If I describe the radii of the disc like I did in this, draw pictures of them. These are probably some of the hardest problems conceptually to think about. Drawing pictures will help you a lot on these. All right, that's one of those type problems what you had in mind, huh? Yeah, there are a couple of others on some of the exams, so really spend some time looking at those. Look, if you just memorize all the questions for the quiz, I'm okay. That's not going to help you much on the exam, but it will help you begin to sort of grasp the material. So y'all have a good day. I know a couple of you came in late, so come see me. I can make sure I get your time.